So let's talk about petrophysical uncertainty. So the best way to understand uncertainty in petrophysics is to consider a new prospect. Think of a prospect that we haven't drilled yet. Now, we can actually estimate the hydrocarbon volumes that may be in this prospect. We can look at the rock properties in similar accumulations nearby. We can look at the size of the trap. We can maybe even use saturation height functions to determine likely fluid saturations. But obviously, if we do this, we have huge uncertainty. And what we're going to do in our petrophysical interpretation is to reduce that uncertainty from the massive amount that we start with to a reasonable, manageable level. So drilling the first well answers a lot of questions. For instance, is there actually any hydrocarbon in this trap? What is the formation? Is it what we expected it to be? And do we get the kind of saturations that we were expecting to see from our initial concepts? And then gradually, as we drill more and more wells, the uncertainties start to reduce considerably until we end up with a prospect that hopefully is worth developing. So when we evaluate the reservoir and we start to go into a development mode, we need to have reliable estimates of a number of properties of the reservoir. And these properties that we see in this list here basically give us the overall hydrocarbon in place. Now, the properties that I've colored yellow are the ones that come straight from the petrophysical interpretation. So these are the ones that are key to us, and this is what we'll be talking about most today. Now, it's often said that the gross rock volume is the biggest uncertainty, and I've even heard people say, well, that's so big that why do we bother with the other uncertainties? But the point is, all of these values, all these parameters are multiplied together. So however uncertain you are in your gross rock volume, if you are also uncertain in your porosity, you're multiplying those uncertainties together. So every component of this equation is important. Now, when we take that prospect and we start to go into development mode, we want to work out how much, what we have there, what the resources are there. And there's various different reasons for accurately determining the volume of hydrocarbon beyond the obvious. So we can see here that we're looking at creating a platform for business decisions, but also looking at raising finance to do the development and going along with the various requirements and regulations that we need to comply with. So because we've got a global business, everything that we do tends to be on an international scale, we need global standards to actually apply so that we can be sure that everybody is reporting properly. Now, the PRMS system, the Petroleum Resources Management System, is increasingly being used around the world as the standard for reporting resources. It was started by the SPE Oil and Gas Reserves Committee a number of years ago now, and it's now sponsored by a large group of professional societies that you can see on the right there, including the SPWLA, finally. It's taken a while to get us on there. And gradually, under the sponsorship of these societies and with a lot of people watching what goes on, the whole system is being improved on a continuous basis. Now, if we go into the PRMS, and we look at the main classification framework for resources, what we see is this slide here, this picture, where we see resources grouped and ranked by increasing chance of commerciality and the range of uncertainty. Now, this is a key to the whole concept of looking at the reserves and the resources that we have, is what is our uncertainty. Now, generally, when we run our calculations on our reservoir model, we make three cases. We look at a best estimate, which is what we think we have based on our best technical interpretation of the data that we have. We also make a low estimate, which is necessary to look at the overall uncertainties, and we have a high estimate to see what the full potential of the prospect is. Now, those three estimates are often called 1P, 2P, and 3P. Sometimes they're called proved, proved plus probable, and proved plus probable plus possible. Also, they're denoted by P90, P50, and P10, where the P number stands for the probability of getting the resources that we're reporting. So P90 would mean we've got a 90% probability of getting a greater volume. Now, sometimes those probabilities are reversed, but in the PRMS, P90 is the pessimistic case and P10 is the optimistic case. So that is the terminology I'm going to be using today. The most important of these is the pessimistic case, this one here, because it's the pessimistic case which is generally used to determine the economic viability of a prospect. And the difference between our best technical estimate and the pessimistic case, the P90, is down to the uncertainties in all of the calculations that we do. So it's important that we get our uncertainties right. Now, another page on the PRMS shows this table here, which is some guidelines for typical ranges of uncertainty. Now, pardon me, these are actually very large numbers. These are very large error ranges. And generally, I think of these as being worst case scenarios. If you were drilling a complete wildcat well in a new area, these may be the uncertainties that you would have. But generally, as we start to develop prospects, we can reduce our uncertainties greatly. But the thing is, if we don't report our uncertainties, this is what will probably get used. And if we look at our volumetrics equation here, and if we just take those guidelines and apply the errors to our reserves estimate, what we find is the difference between the most likely case and the pessimistic scenario is always 45.6%. So imagine we are taking away 45.6% of the resources that we think we have based on our best technical estimate. So this really makes you wonder how many prospects around the world have been abandoned because the incorrect uncertainties were used and the pessimistic case was way too low than it should have been. So really, we do need to get these numbers reported and reported properly. Now, on the other hand, we have the optimistic scenario, which using these numbers will always give us a 65.6% increase in the most likely case. Again, that is way off what we would normally expect. And if we start doing development planning on the basis of that, we could be wasting a lot of money. So what are we actually looking at then? What do we need to look at to identify our uncertainties in petrophysics? I'm just concentrating on the petrophysical numbers here. What we have are errors and uncertainties that can be divided into three groups: random, systematic, and model-based. So if we look at random uncertainty, if we're not sure of an actual value at any given depth because of measurement noise, because of the nature of the measurement, then we have an uncertainty in that value. If we repeat a measurement, we'll find we get different values at each depth. So you can see that for any given depth, there is uncertainty. But when we average these values over an interval to give us, say, the average porosity for a zone that we're going to use in our equation, then what we find is the random noise-based uncertainty is cancelled out. Now, we can't ignore this totally, because when we're picking parameters, like a shale point on a neutron density crossplot, or when we're setting cutoffs to determine what is or what is not pay, we need to be aware of the random noise which is going to affect our results. So it's not the biggest issue, but it can't be ignored. The second one is systematic uncertainty, and this is where there's a bulk shift between a measurement and the true value being measured. In logs, this is often the case if we have environmental effects or calibration errors. Environmental effects themselves can be uncertain. If we run environmental corrections and we put the wrong numbers, the wrong temperature, the wrong salinity, we can get errors which are systematic errors in our final answer. We also have parametric uncertainty, where if we don't know exactly what that formation is, we might have an idea of what the grain density is or the gamma ray for shale is, but we don't know exactly, so that is going to give us a systematic error. So systematic errors can be divided into measurement uncertainty and geological uncertainty. These are key issues, and this is what we're going to spend probably most of our time considering or looking at. The third type of uncertainty that we need to consider is model-based uncertainty. And this is where the interpretation model we're using might not be appropriate for the formation that we're evaluating. If you go through the literature, there are very, very few references to model-based uncertainty. And when it is mentioned, it's often dismissed as just too hard to quantify. However, in my research, I found that quite often model-based uncertainty can be the largest of all of them and the one that we should be concentrating most on. So if we go back to the PRMS, they have three, everything seems to come in threes in this presentation. They have three different general methods for assessing the uncertainties I've just described. They talk about deterministic processes, where we usually use a statistical routine and we end up with three sets of parameters based on modeling of errors. They talk about scenario modeling, where we look at multiple possibilities, and they talk about probabilistic methods, the most common, most used of which is Monte Carlo processing. So with analytical methods, these are statistical techniques that are commonly used in a lot of other scientific disciplines. However, they tend to concentrate on measurement uncertainty and random noise. They don't take into account the complexities of a petrophysical interpretation with some of the dependencies that we have, and we'll go into the dependencies in some more detail in a short while. So while these are commonly used around the various sciences, what we've found is that in petrophysics they're not really appropriate. Scenario modeling is the work where we create many different models taking into account variations in the reservoir properties. So we can look at different facies models, we can look at different porosity or saturation models, and we create large numbers of individual models, each of which is a valid possible interpretation based on what we know from our wells of our formation. Now, each of these can be used to generate a hydrocarbon in place. We can look at the distribution from all the different combinations of scenarios, and from that determine our pessimistic, most likely, and optimistic case. The third of our techniques is Monte Carlo processing. Now, in Monte Carlo processing, each parameter, rather than using a single number, is assigned a distribution of possible values, and this denotes the uncertainty in each parameter. The interpretation is run many times with a random number generator picking a value for each parameter from this distribution each time we run what we call an iteration. So we run the process a lot of times, a lot of iterations, and we get a large number of different answers, and those different answers are displayed on our depth plots like this. The dark blue line is our base case, our first interpretation, the one that we probably think is the most likely, and behind that we'll see those blue distributions of the possibilities of the high and low values. And this is what Monte Carlo processing does, and it's an incredibly powerful tool to actually incorporate all of the actual uncertainties that we know that we have. When we actually run this, then what we see are input curves which have an uncertainty in themselves. This is based on running, say, environmental corrections or looking at possible calibration errors, looking at the accuracy and looking at the accuracy, not the precision of the measurements, and so we take a range of input curves, we take random variations between them for each iteration, and then we create a large range of outputs, possible outputs with distributions. Now, if we have an interval that we're interested in, we can sum the hydrocarbon in place. In this case, we're using the equivalent hydrocarbon column metric, and we can plot that for this interval. So this is one zone of one well where we can see the equivalent hydrocarbon column, and we have the red curve here, which is a cumulative distribution function of all of the possible results that we've created. We also have 3 vertical red lines there, which correspond to the percentiles, which give us a P90, a P50, and a P10 result. And they are plotted on the plot there. So that is for one interpretation method, and that is how Monte Carlo processing will give us uncertainty in our hydrocarbon in place for one interval. If we are not sure about the formation that we have, we're not sure about the exact interpretation style that we should be using, the model, the technique that we should be using, or the parameters, depending on different lithologies, then we should be running different models, different interpretation types, to see what the overall range of uncertainty is, not just based on our parameters or our measurements, but based on our knowledge of the formation. In this case, we can run the Monte Carlo process different times. We've got 4 different Monte Carlo runs to generate SW here, and 4 different versions of the bottle volume of hydrocarbon in the formation. And then again, we can sum those values up and get an equivalent hydrocarbon column for that formation, where we can see all of the different possible models. And again, we have a P90, P50, and P10 case for all the different models. In this situation here, we have a very low oil in place, simply because most of the points in those models didn't pass the cutoffs. So that means if we have this kind of uncertainty, we actually can't book anything based on the P90 case. This is why the uncertainties are so important, and why model-based uncertainty is particularly important. So if we go back to our 3 different types of uncertainty, the best ways to address these is to use Monte Carlo processing, which will actually address both random and systematic uncertainty. And then for model-based uncertainty, we use a combination of Monte Carlo results in scenario models. Now, let's talk about Monte Carlo for a minute, because this is a very important issue here. Monte Carlo processing takes its name from the city in Monaco, which is famous for its casinos and games of chance based on random number behavior. Now, in those casinos, I haven't been, but I've been told, that there are many different games of chance. There's many different ways to lose your money. And in the same way as there are many different games of chance, there are many different ways of running a Monte Carlo process, especially when we're looking at a petrophysical interpretation. Now, the most common way that people run uncertainty modeling in petrophysics is by using a spreadsheet with an add-in, such as Crystal Ball or At Risk. And in this case, what they do is they take the zone averages, and they take ranges of each average porosity, average SW, net, the net volume, and they then use Monte Carlo processing with the random number generator to select values from each distribution to create each iteration. So this is iteration number n. For iteration number n, we can run our equivalent hydrocarbon column equation, and from that we can then take all of the different iterations that we run. So 1 to maybe 1,000 or however many we run, and we then get a distribution of possible equivalent hydrocarbon column. And from that, we can determine our P90, P50, and P10 case. That is the most common way of doing this. It's the easiest way of doing this. And it's certainly a lot better than just using those numbers in the PRMS. So what I'm going to do is do some comparisons of different styles of Monte Carlo processing. And I'm going to use this small field. This is the one I showed at the beginning. It's just a small shaly sand field with 5 wells in it. There's 2 zones producing oil and gas. It's very small and very easy to model and very easy to manage for comparison's sake like this. So in our PRMS guidelines, as I said before, the difference between the most likely or the P50 case and the P90 case is minus 45.6%. So if we come up with an interpretation and we then look for our P90, we're going to be taking away 45.6% of our hydrocarbon in place using those guidelines. Now, if we run that spreadsheet technique, what we find is that we improve we reduce our uncertainties considerably. And in this case, we improve the value of our formation. We've now got 25% more hydrocarbons just from calculating our uncertainties rather than using those guidelines. But there's more we can do. If we take an interval from one of the wells in that field, this is just the lower zone, sand B from the first well, and if we take the average porosity and the average saturation, and we calculate from that the hydrocarbon in place for that interval, we can run the base case, and we can also run a P90 case, or we can run any version of any probability we want, and we see the difference. And in this case, the difference is minus 22.9%. However, we find that that is an issue looking at averages. If we have any form of heterogeneity in the formation, what we find is that those averages are masking some of the variation on a depth-by-depth basis. Over here, we have a cumulative equivalent hydrocarbon column. The blue line is the base case. The distributions behind are fairly clear. And if we go to the bottom of this interval and actually look at what our cumulative values are, we find that the equivalent hydrocarbon column for the base case is very similar, but our P90 case is quite a lot higher. That is because we have dependencies which we are ignoring, and if we run a depth-by-depth process, we actually reduce our uncertainty considerably compared to using zone averages in our spreadsheet. I'll explain this a little bit more in a minute, but just to show you the difference overall in the field of using averages compared to summed values, we can see here that we are again reducing our uncertainties by using depth-by-depth processing, and the more heterogeneous the formation, the greater that difference will be. So another of the issues is the actual style that we use for our Monte Carlo processing. And we've got one method which we would call a modular workflow. And in the modular workflow, each part of the interpretation, from the environmental corrections through calculations of V-shell, porosity, perm, SW, right through to hydrocarbon volume, the bulk volume of hydrocarbon, is run in a separate module which outputs 3 cases, the low value, the mid value, and the high value. And those 3 cases are input to the next module, which then uses the random number generator to determine the value from all the inputs. And this is very easy. It's easy to program, it's easy to run, and it also allows us to do the depth-by-depth calculation, which is summed to get the equivalent hydrocarbon column. But the problem with this, the problem with this is that when we have a function, in this case we're finding y from x, we see the uncertainty in x is reflected in y. Now, if we use a nonlinear function, let's face it, most of the functions in petrophysics are nonlinear, and we get SW from porosity, if we keep all our other values the same and just vary porosity, we see this asymmetry developing. But the other problem here is if we were to put SW and porosity into a Monte Carlo process to then generate hydrocarbon volume, we would be taking the complete range of both of those inputs. And of course, this is invalid because only the points along the blue line are valid data points. So if we use this technique, what we find is we're including a whole lot of data points that are just not valid. Therefore, we are increasing our uncertainty. On the other hand, we can use a single workflow where all of the processes are trained together. So we have one set of logs from our environmental corrections, which are put into every single step of the process. We have one value of V shell, one value of porosity, and each one relates to the previous one. So that at the end, each of our values of bulk volume of hydrocarbon is a valid interpretation. It's not just randomly selected from distributions. We also note that we're not seeing nice regular distributions here. We're seeing actual distributions, as they are in the formation. So this allows the petrophysicist to automatically account for that type of dependency. And that type of dependency is also the type of thing that we see in the zone averaging. These are two dependencies that are very similar. So if we run everything in a single workflow chained together, then what we find is that we have a much improved result. So whereas our modular workflow for this formation gave us a difference between the most likely and P90 of 14%, using a single workflow, we can reduce that to reduce our uncertainty by about a third and add 10% to the value of our formation. Now, it doesn't stop there. This is another parameter dependency that we have that we need to take into account. In this case, if we make an estimate of say, a shale point on a neutron density cross plot, we can put in uncertainty around that estimate. That's fine. But the problem is, as we are inputting uncertain logs, our data points are going to move every iteration that we run. So really, our picks are going to be invalid as soon as we start moving the input data. Let me explain that a bit better with another example. If we have a picket plot, and on our picket plot, we've got a water leg, we've got an oil zone, we've got a transition zone. This is all very familiar to most people, I'm sure. If we have a value of RW, we can draw a line through our, sorry, my animation's disappearing. We can draw a line through our clean sand water points, say that that is 100% SW. We say the gradient of that line is M, and based on N, we can determine the saturations of our various different clean sand points. Nice and simple. Now, we can also put an uncertainty on our M value. That's easy as well. The problem arises when we start to consider the uncertainties in the input data. Because let's just imagine that we've got P90 and P10 versions of each of our input curves, and we take the P10 version of porosity, the P10 version of resistivity. Of course, our data points have to move to cope with the P10. And if we just look at the P10 for the 100% water line, that should go through our P10 version of RW. So that needs to move out there. So it's quite clear then that what we're doing in the P10 case is overestimating the hydrocarbons in place, including putting a lot of hydrocarbon in our water leg. On the other hand, if we look at our P90 case, our pessimistic case, and we take a P90 porosity, P90 resistivity, and we move our data points down there, and then we match our 100% water line to the RW, the P90 RW, what we're finding is that we are underestimating our hydrocarbons in place. So if we ignore these dependencies, because this is a dependency in the calculation from the variations of the input, if we ignore those, our optimistic case is overestimating, our pessimistic case is underestimating. Therefore, we are overestimating our total uncertainty. So what can we do about this? What we do in Geolog is to automatically adjust those picks for the movement in the data. So in the first iteration, we might have our data points there. We have an M for our first iteration, and we have uncertainty on that M. For our second iteration, our data points move down there, so we match the M to the movement in the data points, and then we apply the uncertainty range to that value. And we do this over and over again for all of the different iterations that we run. And in doing so, we're honoring the original pick of M by the petrophysicist. We're reducing the calculated effects of uncertainty. So overall, we're going to get a better result using this technique than if we ignore the technique. We're going to reduce our uncertainties. But we can only do it if the correct type of Monte Carlo processing is applied. Now, I already mentioned the modular and single workflow. We can only do this with a single workflow because in a modular workflow, the points don't move as a group. They move randomly, separately from each other. I'll talk about the other difference in a minute, but just to complete our comparisons, if we run a single workflow with auto adjustment on our field that we're looking at here, we find we reduce our uncertainty even further. Now, what I've got to stress here is that these values are all based on the same interpretations, using the same parameters and the same uncertainties. The only thing that's different is the way that we're actually looking at our uncertainty, the way we're doing a Monte Carlo process. That's the only thing that's changed, from the spreadsheet down to the single workflow with auto adjustment. But if you take this overall change, in this example, the value of the petrophysicist correctly modeling uncertainty was more than 40% of the best estimate of hydrocarbon in place. This is the difference between the petrophysicists doing their uncertainty and the modelers using the PRMS guidelines. And as you can see, that is a really good justification for the petrophysicist's existence. Now, the final different way of running Monte Carlo is this. We have what we call horizontal and vertical processing techniques. In a horizontal processing, we've got our depths and we've got each of the iterations. We run the random number parameter selector and we do our calculations. And in this case, we are filling in our table horizontally. So we call this horizontal processing. This is apparently the most common technique for Monte Carlo processing, and it's available not just in petrophysics, but in a lot of different places. The alternative is what we call vertical processing, where here we run our random number generator or random parameter selector, and we hold those values for each iteration. Then we run the random number generator again and run the second iteration and the third iteration, and so forth. And because we're filling in our table vertically, we call this vertical processing. Now, at the start, they might not look too different, but the more you think about it, the more these different techniques have a huge impact on the results. The main one being that in this iteration, we have one set of parameters. So that means that that iteration is a valid interpretation in its own right, as is that one. In the horizontal version, we don't get that. We just get a cloud of uncertainty in our results, which we can't do anything with. So when we come to compare the two, we find that horizontal processing copes with random uncertainty very well, but just the same as vertical processing. There's no difference in the results. But as soon as we look at systematic uncertainty, as soon as we try to output specific cases of probabilities, and when we get into things like sensitivity analysis and parameter dependencies, horizontal processing simply doesn't work, whereas vertical processing ticks all the boxes. So we can summarize this by saying we can use horizontal processing and vertical processing with modular or single workflows. The horizontal processing doesn't allow us to calculate a P50, P10, P90 case because we've just got random noise in our interpretations. Only the vertical processing will allow us to have individual cases that are valid. But if we use a modular workflow, we can't address all of the dependencies. So we're always going to overestimate our final uncertainty. So the only way that we should be working to get results to go into a reservoir model is using a single workflow with vertical processing. And if you're a Geolog user, which I believe all of you are, then you're lucky because you can do that in Geolog. I'm not sure that there is another system which allows this, which is scary because it means that most of the petrophysical uncertainties out there are actually overestimated. So let's just summarize. Modeling of petrophysical uncertainty must be done by the petrophysicist. We shouldn't be leaving the reservoir modeler to take guidelines or just to guess what the uncertainties will be. We have to do this ourselves. We need to consider all aspects of uncertainty and model them accordingly, not just random noise, not just measurement error. We need to think about our geological uncertainties too. It's best to use a combination of Monte Carlo and scenario modeling. Monte Carlo modeling lends itself to straightforward interpretations. Scenario modeling can also help us with things like free water level uncertainty, saturation height function uncertainty. Various things that don't lend themselves to Monte Carlo processing can be done in scenario modeling. So if you use a combination of the two, you're always going to get the best results. If you're using Monte Carlo, it's critical that you use the correct form. Don't just assume that Monte Carlo is the same everywhere, because it isn't. That would be like saying that all the games played in Monte Carlo, like roulette and blackjack, are the same. They aren't. Use scenario modeling, as I said earlier, for different interpretation models, contact uncertainty, etc. And when you get the results, you have to report them correctly, and you have to be sure that the person using them in the reservoir model understands them. You can't just say, oh, this is my P90 porosity, multiply that by my P90 SW to get my P90 bulk volume hydrocarbon. That's wrong. You've got to understand the results you're reporting, and you've got to be sure that the person using them in the model understands them as well. And finally, uncertainty modeling can also be used to define the value of information. It can be used to define how much that extra log or that extra piece of core is actually worth in monetary terms. But I'm afraid we don't have time to go into that today. That's a subject for another day, or maybe for the training course, if you want to go into this in any more detail. So that concludes my short presentation for today.